Okay, to begin with capacitors, we're going to look at what a capacitor is and what capacitance is and how we can work that out. So basically, a capacitor is just a way of storing and then releasing charge. And you have two metal plates in parallel with a battery or some other charging device enabling a differential charge to build up across it. And when we say that a capacitor is storing charge, what we actually mean is that it has a positive charge on one side and an equal negative charge on the other side. So you get a potential difference across your capacitor. Now, when you're charging up a capacitor, and for this we're going to say that we're managing to keep the constant current, we'll look in a little bit at why that would be difficult to do. But using a circuit like this with a variable resistor, you can change the resistance of that resistor to keep the current in the circuit constant. So that means your battery can deliver a constant current, a constant flow of electrons to the capacitor, allowing a constant build-up of electrons on one side and build-up of protons on the other, because the electrons will flow away from the capacitor in order to continue the charge. So at any time, if you've got a constant current, the charge stored on the capacitor is going to be equal to the current times the time, IT. But what's happening to the potential difference of the resistor? Well, again, assuming constant current, as you add an electron to one side, you're gaining a corresponding proton to the other side. But this is happening at a constant rate. So the potential difference across my capacitor, if I have constant current, is going to rise constantly. And if I were to represent that in a graph of charge against the PD across the capacitor, I get a nice straight line. Now the gradient of that straight line gives me a really important factor for my capacitor, and that is the capacitance of the capacitor. Now, the capacitance is just the ability of a body to store charge, but for your exam, you also need to be able to state that the capacitance is the charge stored per unit potential difference. That's the official AQA definition. And so remembering that the gradient is the capacitance, and that's an important thing to remember, they will often ask that in the exam. What do you get from the gradient of a charge potential difference graph? The unit of the capacitance is the farad. And if you want to think about what that would be in SI units, well, you've got charge divided by potential difference. So you have coulomb volts to the minus 1, coulombs per volt. But 1 farad is actually a really large value. Usually when we're dealing with everyday capacitors, we're looking at things in the microfarad or even smaller. Now the big equation that we obtain from this graph is that the gradient is equal to your charge Q divided by your potential difference V. So C, which is our symbol for our capacitance, is equal to Q over V. So let's have a quick look at an example question then using those basic things. If a 20 microfarad capacitor is charged with a constant current of 2.5 microamps to a potential difference of 12 volts, calculate A, the charge stored on the capacitor, and B, the time taken to charge it to that potential difference of 12 volts. Well, we just learnt that C is equal to Q over V, so if we rearrange that, we get that Q, which is what we're looking for, the charge stored, is equal to CV. Now we know that the capacitance is 20 microfarads and we know that the voltage is 12. So plugging those into my equation, I get an answer of 240 times 10 to the minus 6 coulombs. How long would it take to get there? Well, to work that out, I'm going to have to use Q equals IT. Charge is current times time. I have the charge, it's what I worked out in the last question. I have The current, I'm giving it as 2.5 microamps, and time is what I'm looking for. So if I rearrange that equation to make t the subject, I can then plug my numbers in to give me an answer of 96 seconds. We have a look at example 2. A capacitor is charged by a constant current of 0.5 microamps to a potential difference of 5 volts, and it takes 55 seconds to do that. First thing it wants to know is the charge stored. Well, Q is IT, and if we have a look, have we got everything we need for that? We have a current, and we have a time of 55 seconds. So when I plug my numbers in, I end up getting an answer of a stored charge of 2.75 times 10 to the minus 5 coulombs. So what would the capacitor be? Well, we go back to our capacitance equation. C equals Q over V. I now have a Q, I've just calculated it, and I know that it's been charged to a PD of 5 volts. So I substitute those into my equation, and I get an answer of 5.5 microfarads.